We've surveyed over 3,000 American adults, and we've concluded from that data that 74% said they use the internet. Is it valid to report that 3/4 of all adults use the internet? And so, first things first, we're going to determine our null and alternative hypothesis. Remember, in order to do that, we're going to want to assess the claim first, and the claim is that 3/4 of all adults use the internet. So again, as a reminder here, we will have a claim or hypothesis involving a parameter, and notice we've indicated that right here with the usage of the word all. We know this is a proportion problem, not just because that's the section that we're in, but because we're dealing with a certain number of people who responded yes to something as a quote success, and another set of people who've responded no as a quote unquote failure. So the claim would be that P is equal to 0.75. Notice that's not asked anywhere. It's not really part of the problem. You want to make a note of that to the side, that we're saying that the claim is that P equals 0.75. And so because of that, that leads us to our null and alternative, like so. Then we have our conditions, our assumptions that we have to check. Again, this could go here, this could go at the very end of the problem. Doesn't matter where it goes, as long as it goes somewhere. In every single problem, no matter what, we are always going to check to see if we have a representative sample. We're not going to make up something that isn't there, but we're going to note what is there. And in this case, what I notice is that we are trying to make an inference of all adults, but make sure we note that the sample data only contains results from American adults. And so since that's the case, we can only make an inference on American adults. Okay, so there's nothing necessarily wrong with the sampling. It's just that we cannot make a conclusion about all adults. We can only make a conclusion about American adults. Otherwise, we would have sampling bias there because we don't have people from other countries. So no matter what, we're always going to check to see if our sampling is representative. That is step one here in the assumption check. Then step two, we're always going to look at our mathematical assumptions. Again, for means problems, we have to look at if X is normally distributed. If not, we check our sample size relative to the skewness to see if X bar is normally distributed. For a proportion problem, we have three things to check. All three have to hold. We have to show that X follows binomial distribution, and we have to show that N times P naught and N times Q naught are both sufficiently large. If all three of those hold, then we say P hat is approximately normal. Again, why is that important? Because that's the statistic we're going to standardize. And as we talked about before, when we standardize a statistic that's normal, that's what gives us our 1-2 punch of standard and normal. It lets us convert that to a Z statistic and go to our Z table for critical values and P values. It's the whole ability for us to find these mathematical answers relies on, did we standardize something that was normal? So we have to show that our test statistic, that the base of that P hat is actually normally distributed. So we check all three of those things. All three of those things do look good. Now make sure that when you work these problems, you don't just say, yes, X follows a binomial distribution. You actually check that. Because if you just write that down every single problem, eventually you're going to get one of those wrong, because that's not always going to be true. We want to check all four of those characteristics. We have a fixed number of trials. We have 3,011 trials. That's how many people we've asked. There are only two options. Do you use the internet or not? They can't happen at the same time. You can't both use the internet and not use the internet, right? They are mutually exclusive, so that's two. Is the probability of success constant from trial to trial? There's no reason to think otherwise. Now, if this said that these 3,000 adults were at over a period of 10 years, then you would say, no, the probability of success is different because 10 years ago, the likelihood that someone uses the internet or not is different from today. But that's not the case here. We don't have anything to tell us that there's any difference. There's no time component of this. So I would say, sure, the probability of success stays constant and other trials independent. Yeah, I'd say that whether the first person uses it or not does not change the next person, right? Again, we want to think through this. We don't want to overthink it, right? When we had that airplane problem previously, we said, well, we know that families fly together, and if one person doesn't make it to the airport on time and misses the flight, they might be traveling with someone, right? So that's kind of a common thing to think about. Here, there's nothing that would indicate to me why, if one person says yes, the next person will be more or less likely to, right? And I would have to see something in the problem that said, when we sampled groups that were, people that live together or something. If you saw that, now you might think, well, if people live together, they're more or less likely, right, that whatever happens to one affects what's happened to the other because they're, part of the same family. But we're not going to add anything in like that unless it's, apparent. And there's nothing like that here. So I go through all four of those characteristics. I say, looks like X follows binomial distribution, no big deal. We check the math on n times p naught and n times q naught. And those both check out as fine. So we can conclude that p hat is approximately normal. And then we move forward with finding our test statistic, because this is a proportion problem that will follow a z distribution, and we standardize value minus mean over standard deviation, just like always. And then we just plug in the numbers. The biggest thing here, make sure we understand the difference between 0.74 and 0.75. Make sure we know which one's p hat and which one's p naught, right? We know that the p hat is a sample proportion. It's going to come from the data. P naught is the hypothesized population proportion and is going to be attached to some population word, all known, real, true, something like that. So make sure we can identify the difference between those. One of the common mistakes is students will put 0.74 in the null rather than 0.75, and they'll crisscross them here, and that'll lead to an incorrect answer. Once you plug the numbers in, it's just following the math from there. You should be able to easily arrive at the following answer. And so next steps is find the rejection region and or p-value. In these example problems, we are going to work all the problems both ways via the rejection region and the p-value method. I'm going to show you how to do both for the examples. When you get to the exam, you may see a problem that doesn't specify and just says solve the problem. You can do it whichever way you want. Or you may see problems that say work it using the rejection region method, or a problem that says work it using the p-value method. So you need to know how to do both. In the examples, we're going to do both, but in any individual problem, if it doesn't tell you to work it both ways and it doesn't tell you how to work it, you can work it whichever way is your favorite. If it says work it one way or the other, then just work it that way. There's no need to work it both ways. I'm just doing it to show you because you need to be good at both. So as we go through this, if one of them seems easier, then you can kind of cool that, and then spend a little more time on the one that is not your preferred method. So I'm going to start with the rejection region. I'm going to draw a picture like so. Now I'm drawing a generic picture because these are in slides. In reality, you should draw a picture that matches the scenario of the problem. Notice here we have a two-tailed test. How do I know that? I know that from the alternative hypothesis. It's a not equal to hypothesis. And so that's a two-tailed test. And what I'm going to do is I'm going to take my alpha and I'm going to split it in half, put some on both sides. Now you look up at the problem and you say there was no significance level given to us. If you're given a significance level, hallelujah, nice and simple. It could be the word significance level. It could be the symbol alpha. That's fine. If you're not given one, we are going to default to a significance level of 0.05. If you don't know what the significance level is because it doesn't tell you in the problem, we just default to 0.05. So in this case, dividing 0.05 in half is 0.025, and I would put 0.025 in the right tail, 0.025 in the left tail, and this value right here and this value right here are the values of plus and minus 1.96. And then, because I've labeled this right here as 1.96 and this as negative 1.96, I can draw negative 1.25 goes right somewhere in here. It doesn't have to be a scale, again, because this is a number line. So that negative 1.25 is somewhere over here, clearly not in the rejection region, which means later on I know I'm going to fail to reject because I didn't land in the rejection region. Also, though, we're going to work it the other way. We're going to work at the p-value method. Again, the answers should align. If they don't, you got a problem. Because I have a two-tailed test, I know I have to multiply by p-value by 2. The only question is, what is the symbol that goes in my probability statement? And again, if we have a right-tailed test, we do greater than or equal to. We have a left-tailed test, we do less than or equal to. If we have a two-tailed test, we go the direction of the sign of the test statistic. Our test statistic is negative. And so we're going to do a less than or equal to p-value, like so. Look that value up in the table, multiply by 2, and we can get the p-value. And so as we talked about before, we knew from the rejection region method that if our test statistic is out here in the middle area, that we would fail to reject. Also, our p-value is large, definitely larger than 0.05, which is our alpha. Notice, remember here, we don't compare this to alpha over 2, right? We multiply by 2. We took care of the 2 part already. So now we just compare it to alpha, which is 0.05. And so because our p-value is larger than our alpha, we also fail to reject. So we've got the same answer both ways. That's good. So then we're going to come back and we're going to say, did we reject or fail to reject? Well, we're going to fail to reject. Want to justify it? Why? Okay, and so I'm going to put both answers here. Again, if you work the problem only one way, you'd only have to put one, but I'm going to say because our test statistic did not fall in the rejection region and our p-value is greater than alpha, we fail to reject the null hypothesis. And because we have failed to reject the null hypothesis, what does that mean about the alternative? Again, you can say it one of two ways. You can say there is not sufficient evidence to conclude the alternative, or you can say we cannot conclude the alternative. Either one's fine. So I'm going to close the problem off with the 5% significance level. There is not sufficient evidence to conclude that the true percentage of American adults who use the internet is different from 75%. And this is where we talked about last time. There are a lot of different pieces that need to go into this conclusion with regards to the alternative. You don't get to write alternative hypothesis. You actually have to write it out in words. Notice right here, we've used a population word, true, could have put all, could have put population, could have put real. Had some options there. Percentage, could have said percentage, could have said proportion. Either one's fine. Just take note, if you say percentage, you should write that as a percentage. If you say proportion, you should write that as a decimal. Of what? Like we said, we have to say a population word. We have to say what metric we're using, and then of what. Right, so you can't just say true percentage. True percentage of what? True percentage of American adults who use the internet. That's the context of the problem. Go back to what the problem asked you to do to get that. Right, so true percentage of American adults who use the internet. And then this is where we say the alternative hypothesis is not equal to, and so we're going to use the phrase different from. If the alternative was a greater than, we would say is greater than. If the alternative is less than, we say is less than. If it's a not equal to, we say is different from. Again, that just avoids a double negative, rather than saying not equal to, because we'd have not and not. So that's why I use the word different from 75%. That part is important there too, because the number 0.75 was in the alternative hypothesis, so we couldn't just forget that.